Hello students and welcome to Lesson 3 of Unit 5. In this lesson we are going to continue learning how to decide if a relationship is a relation or a function. So to complete this lesson you will have to answer two essential questions. First, what are relations and functions? And second, given a relationship's ordered pairs, table, or mapping diagram, how can I decide if it's a relation or a function? So let's first review what we've learned so far. We have learned what a relation is. We know that a relation is just a relationship between two sets of independent and dependent variables. So if a relationship exists, then it's called a relation. Any link between two sets is called a relation. We have also learned what a function is. We know that a function is a relation because it represents a relationship, but it's a special type of relation because every input has one and only one output. And that fact right there will be the basis of how you will make decisions about ordered pairs, tables, and mapping diagrams in this lesson. So as we have talked about, we are going to be looking at sets of points, tables, and mapping diagrams and trying to decide if they are a relation or a function. So to build some background information, I first want to show you what each looks like. If a relationship is organized as a set of points, you will see ordered pairs just like the ordered pairs that you graphed on the coordinate plane. The x value of a point represents the input, and the y value of an ordered pair represents the output. So this ordered pair here would say if you input 4, the output will be 5. This one would say if you input 5, the output would be 7. And so on. So anytime you see something organized as a set of points, you will know that it will be ordered pairs in which the x value is the input and the y value is the output. A table can organize the same ordered pairs. However, it is organized in a two-column or two-row table where one represents the input and one represents the output. You can at times see this as saying X or Y because we know that X's are the inputs and Y's are the outputs. The third way is the mapping diagram. The mapping diagram uses arrows to show the connection between two numbers, the inputs on the left and the outputs on the right. If you think about it, inputs come before outputs, and just as we read from left to right, so a mapping diagram is read. Now, let's start looking at how we can decide if a relationship is a function or not if we're given a set of points. So let's look at a real-world example to be the basis of our start. In the scoring system of some track meets, for first place, a runner gets 5 points. For second place, a runner gets 3 points. For third place, a runner gets 2 points. And for fourth place, a runner gets 1 point. This scoring system is a relationship because there is a relationship between the place value that you earn in the race and the number of points you earn. Now, that same scoring system that I just read to you could be described by these set of ordered pairs. If you get first place, you get 5 points. If you get second place, you get 3 points. If you get third place, you get 2 points. If you get fourth place, you get 1 point. So ask yourself, is this a relation or is it a function? In the previous lesson, you would say, this is a function because it's predictable. If I think I'll get first place, then I'll know I'll get 5 points. But if we think more specifically about the layout of these ordered pairs, does each input have one and only one output? In other words, does first place always output 5? And the answer is yes, because we do not see another input of 1. Does an input of 2 always output 3? Yes, every time you get second place, you'll get 3 points. Does an input of 3 always output 2? Yes. If you get third place, you will always get 2 points. And last, does an input of 4 always give you an output of 1? And the answer is yes. So, does each input have one and only one output? Yes. So that is a function. I didn't write that in a complete sentence, but you can imagine that you could. You could say this relationship is a function because every input has one and only one output. Let's look at some more examples. Here we have another set of ordered pairs, and remember the question we're going to ask ourselves is, does every input have one and only one output? So let's start here. Does this input of 6 always output -1? Do we see any other inputs of 6? No. So 6 must always output -1. Does 5 always output 0? Well, do you see any more inputs of 5? No, so that must mean that 5 always outputs 0. Does 2 always output -4? Do you see any other inputs of 2? No, so this must always output -4. And last, does 1 always output 0? Do you see any other inputs of 1? No. So, sorry, mark this one backwards. So, 1 must always output 0. Now notice, 5 and 1 both have the same output. That's okay. It's every input that matters. So it does every input have one and only one output? And the answer is yes. So this is a function. Let's look at another example. Remember, we're asking ourselves, does every input have one and only one output? So let's start here. Does the input of 1 always output 1? Well, do you see any other inputs of 1? Yeah, here's another input of 1, but it's outputting 6. So that tells us that an input of 1 can output 1 or 6. So does every input have just one output? And the answer is no. So that means this is just a relation. There is still a relationship between the points, but it's not a consistent, reliable one because the input of 1 has more than one output. Let's look at two more examples. Let's look at the first one. We have an input of 9 and an output of 8. Does an input of 9 have only one output? And the answer is no, because we see this other input of 9 outputting 3. So in other words, an input of 9 can output 8 or 3. So does every input have just one output? And the answer is no, so this is a relation. There's a relationship between the points, but it is not a function since one of the inputs has more than one output, and we don't even have to check the other ones once we see that. Now let's look through this second example. Does -3 always output -4? Well, do you see any other inputs of -3? No, so it must have only one output. Does -2 always output 5? We don't see any other inputs of -2, so it must always output -5. Does -1 always output 6? We don't see any other inputs of -1, so it must always output 6. Does an input of 0 always output 7? Well, we don't see any other inputs of 0, so it must always output 7. Does an input of 1 always output 6? Yes. Does an input of 2 always output 5? Yes. So is this a function? Yes, because every input has just one output. We don't see any repeated inputs. Now, this strategy of looking at ordered pairs does have its benefits and drawbacks. Some of the benefits are that it organizes the relationship numerically. So instead of just thinking about the relationship as predictable or unpredictable, we can now see the numbers that represent the relationship. However, it does have a drawback. We know that many real-world relationships have many possible inputs and outputs, so not all of them could be listed as points in a reasonable way. It could become a very, very long list. Now, let's transition to looking at a table. Looking at a table is very similar to our strategy for ordered pairs because a table is another way of writing ordered pairs. For example, if we had to look at the buses needed for a field trip, and we said if you have 25 students, you need one bus. If you have 45 students, you need two buses. If you have 65 students, you need two buses. If we have 85 students, we need three buses. And if we have 105 students, we need three buses. You can see that these are relationships between inputs and outputs. It is a vertical way of organizing the ordered pairs, the x's and the y's. So you can use the same strategy. Every time there's 25 students, will I need just one bus? Yeah. Every time there's 45 students, will I need two buses? Yes. Every time there's 65 students, will I need two buses? Yes. Every time there's 85 students, will I need three buses? Yep. And every time there's 105 students, will I need three buses? And the answer is yes. So this is a function because every input had just one output. We did not see any repeated inputs in our chart. Let's look at another example. You can burn 6 calories per minute, and there you see the constant change that makes it predictable. So you already know this is a function. But if we look at it as a table, we can see there are no repeated inputs, so that must mean that every input has just one output. And I'm just showing you a visual of what's coming next. So, since every input had just one output, this is a function as well. Oops. Let's look at some basic tables out of context. So, we have this table. We have inputs of 3, 5, 2, 8, and 6. So do you see any repeated inputs? No, so that must mean that every input has just one output, so this is a function. There are no repeated inputs. Now let's look at this example. We have inputs of 2, 2, 3, 3, and 4. Do we hear any repeated inputs? And yes, we do, and we can see that there are two inputs outputting two different things. An input of 2 could be 1, or an input of 2 could be a half. So this is a relation since one input had two outputs. Let's look at two more examples. In this example, we have inputs of 4, 0, 2, 0, and -4. Here we see the same input and resulting in two different outputs. That makes this a relation because one input has more than one output. Now let's look at this one. We have no repeated inputs, so that must mean that every input has just one output, making this a function. There are benefits and drawbacks to a table. I want you to take the time to read these yourself and add them to your guided notes. The best benefit is that it clearly separates the inputs and the outputs, which the ordered pairs could not do.